G'day. Welcome to Crystal Clear Mathematics, where it is easier than you think. I'm Graham Henderson. This is the very first in a series of videos about how to graph parabolas. Now, or more precisely, how to create the graphs for quadratic equations. Now, a lot of students I've encountered find difficulty with this. So, if you do, then I'm going to encourage you to watch the entire series, and there will be a number of videos. I'm going to take you step by step through the journey, and the first is just this one, to deal with a little bit of terminology. First of all, the equations that we have are called quadratic equations. The graphs they create are called parabolas. Or at least that's the name of the curve on the graph. We put arrows on to show that we're intelligent people. We know they keep going forever. And the other thing that we use often in our graphing procedure is something like this, with some values in, which is called a table of values. Now, over the course of these videos, I'm going to show you how to make a connection between and understand what's going on between these three things. The first thing to describe, first of all, is why they're called, not so much why they're called parabolas, but what a parabola is. Now, I'm going to show you in much more detail in a later video, but a parabola is defined in this way. If you have a straight line and a point that is not lying on the line, and you are curious, you ask yourself the question, where are the points that are the same distance away from that point there as they are from the line? Well, wherever the point is, its distance from this point is going to be a dead straight line, always to the same point. But the distance from the straight line is going to be a perpendicular line. So as it gets closer, it'll be to this point, and then over here it'll be to this point, but it'll always be a perpendicular line down to this line here. And I think you can see that the point here, right halfway between the two, if I just draw those lines, put a little marker on them, it's the same distance from the point and the line. I should put a little right angle there. I think also, if I drew a square, so that this length and this length and this length and this length are all the same, that you can see that this point will be the same distance from that point as it is from the line, again with a right angle. I think you can see if we put a square on this side, that the same thing would apply. So all of a sudden we realise these points do not lie in a straight line. It turns out that as we plot more and more of them, where the distances are the same, we find they lie in a curve like this. And the Greeks call them parabolas. And that's what we study. Now, because it's using a distance formula all the time, a distance of a point from here and a distance from here, you might recall that the distance formula is based on Pythagoras' theorem, which is based on square numbers. And it's why, you just have to trust me at the moment, later video will show why, but it's why the equations for these curves end up having squares in them, because the squares make the bend. If there was no square, these kinds of graphs would give us straight lines, and the x squared gives us a bend. But that is the nature of a parabola. We're going to push that aside for a moment, because we're going to come back and visit this in some detail in later videos. But for the moment, just pretend, well, not pretend that it never happened, but just be aware that's why we use that definition from geometry that gives us these graphs. Let's study y equals x squared a little bit. I think I might clear the board so we can see this with some clarity. For our next step, we're going to understand what happens with square numbers, because the whole of parabolas, or our understanding of parabolas, is built upon them. So let's examine these. The ancients were very, very familiar with these. They had to measure up land and so on. They were familiar with multiplying numbers. So I'm not going to go a long way down here. In fact, that's probably plenty. We'll just do one more. These are our square numbers. And by the way, if you want to get very, very good at handling parabolas, I encourage you not only to know your multiplication tables, but particularly to know your squares. Now, why are they called square numbers? Well, the Greeks realised that you could make squares with these numbers. Here in Australia, we have a television station called Channel 9, and their logo, their symbol, is this. It's got 9 dots, it makes a square. And here we've got 16. So those don't crowd in together, I'm going to draw this one off to the side. And I don't think I'll go on with 25, it's just a bit of overkill. But here are 16 dots making up a square, and 25 will be 5 by 5. What I want you to notice is this, because it will help you with your graphing. To get from 1 dot to 4 dots, we actually add on a little L shape. And then when we've got 4 dots, if I want to make it up to 9 dots, I add another L shape. And then to get from 9 dots to 16 dots, I add an L shape. And you can see that basically every square is made up of a collection of L shapes, just stacked on. And we can just add another one and another one and another one and build our square up. Now, what's the nature of these L shapes? Well, this one's worth 3 dots. This one's worth 1, 2, 3, 4, 5. This one's worth 1, 2, 3, 4, 5, 6, 7. Now, I hope you notice they're all odd numbers. Not only are they odd numbers, but they're the odd numbers. Nothing's missing. In fact, when I go from no dot to 1 dot, you can say I've added on 1. So 1, 3, 5, 7, the next one will be 9, 11. Why are they odd? Well, I think you can see, I hope you can see that when you add on one of these shapes, which by the way has a name, these L shapes are called a gnomon. You don't pronounce the G, it's not gnomon, it's just a gnomon. It's the same name, by the way, for that little bit that sticks up on a sundial. That sort of L-shaped little post in a sundial. So if you really want to show off someday when you're in a park and you see a sundial, you can say what a lovely ornate gnomon is there. But that's what it's called. Why is it odd? Well, I think you can see that you're always going to have a spare dot in the corner. This number here and this number here, these two numbers are always going to be the same number of dots because you're expanding on a square which has the same sized side on each side. So here you're going to have 3 dots here and 3 dots here and an extra one in the corner. And the same, next one will be 4 dots and 4 dots and an extra one in the corner. So adding these little gnomons on to build up your squares means that you're adding odd numbers. I don't know whether you've ever noticed that. But have a look. From 0 to 1 is a gap of 1. Actually, I should do these in red. That's a gap of 1. From 1 to 4 is a gap of 3. From 4 to 9 is a gap of 5. 9 to 16 is a gap of 7. 16 to 25 is a gap of 9, and so forth. I think if you add 11, you can see that the next number is going to be 36. And if you add 13 to that, you can see the next number is going to be 49. Which means that every perfect square is going to be the sum. Oops, I left out 9. That was a bit of a shame. Is going to be the sum of the odd numbers up to a certain point. That's rather special. Now we can explore that, and we will probably in other videos for other reasons. But how does that help us graph a parabola? Well, it helps quite a lot, and I want to show you. Let's have a look. Let's first of all have a close look at this. We're going to draw up a table of values from our equation. Now I'm using the most basic equation for a parabola we can have, y equals x squared. 0 squared is 0, 1 times 1 is 1, 2 2s are 4, and 3 3s are 9. They're the numbers we discussed in our last little segment. What happens here with the negative numbers? Well, you might recall that a negative number times a negative number makes a positive. So when we calculate minus 1 squared, we get minus 1 times minus 1. Now the 1 is 1, but the minus times minus gives us a plus. So it's not negative 1, it's plus 1 here. What is minus 2 squared? It's minus 2 times minus 2. The 2 2s are 4, and the minus times the minus gives us a plus. Same with 3. Minus 3 squared is minus 3 times minus 3, which is plus 9. So the fascinating thing about this is that even with all these negative numbers down here, we don't get negative answers. Not with this basic one anyway. If we graph them, we notice something quite interesting. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll go that high. Oh well, we'll fill them all in. There we go. Now, 0, 0 is here. The point 1, 1 is here. So when x is worth 1, y is worth 1. When x is worth 2, y is worth 4. And when x is worth 3, y is worth 9. You can see we get a curve. On this side, notice we have minus 1 squared gives us plus 1 again. Minus 2 squared gives us plus 4. And minus 3 squared gives us plus 9. And it's because the two minuses make a plus that our graph doesn't head way down in the negative region. It actually bends back up again. And as the numbers grow, here, when we square them, they grow even more rapidly. So it bends quite steeply upwards. So by the time we get to 5, 5 squared is 25, which is way up above the board. And by the time you've got across to 50, you're up to 2,500. So it accelerates upwards very rapidly. Now when you graph these, I'm going to talk a little bit about the structure here, but when you graph them, on paper, I like to turn the paper so that my hand bends the natural way at the wrist. Don't have a point here at the bottom. If you are in a test, I know because I've marked lots of tests, if a student does that with a point at the bottom and calls it a parabola, they're not going to get full marks from an examiner. A parabola has a rounded bottom down here at the tip and travels up like this, and then I turn the paper, and now it's a bit hard for me to do here, so you'll just have to bear with me. There we go. Another thing to watch out for. Not only is it not good to put a point on the bottom, you can round that off, but don't have your graph go out that way, and even worse, don't have it point back in. Parabolas do not do that. They just continue up with a slight bend, and you put an arrow on to show that they continue. So that's what we will do. Please take care with your graphs, because if you do that on a graph in an exam, you will lose marks if you're marked properly. This demonstrates that you understand what a parabola is. Now, why have I gone to all this trouble? For a few reasons. One, remember our gaps. Our gaps were that when the x value kept jumping by 1, so 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3. The y value jumped 1, and then it jumped 3, and then it jumped 5, and then it would jump 7, and so on. Look at how this will help us graph. If we start at the tip, and by the way, I should introduce the right terminology now. The tip of a parabola has a name, vertex. It's the same word that we use in geometry for the tip of something, or the corner of a triangle or corner of a square is a vertex. That's the same term we give to the tip of a parabola. If we start at the vertex and go across one, we go up one square. If we go across another square, we go up 1, 2, 3 squares. And if we go across another square, we go up 1, 2, 3, 4, 5 squares. Here's the pattern, 1, 3, 5, 1, 3, 5. And guess what's going to happen on this side? Back 1, back 1, up 3, and back 1 and up 5. So if you know your odd numbers, and let's face it, if you're in high school you've got to know your odd numbers, this is a nice way to graph your parabola without having to plot all these individual points. I hope that makes sense. Now we're going to go on from here. I think there was something else I was going to share, but it'll all get picked up. I ad-lib these videos because I just find it easier. I just feel like I talk with you. That's the basic structure for a parabola. I'm going to remove this, or at least erase it, and then I'm going to show you what happens when the parabola is modified slightly. And then we might call that quits just for this particular video. Okay, let's have a quick look. So here I have two parabolas. We're going to do them side by side to compare what's happening. And as you see, we've just changed it very, very slightly. This one is 2x squared, this one is half x squared, so we're changing the coefficient of x squared, the number in front of x squared, to see what it does, how it alters the shape. Well, let's calculate, let's fill in the boxes and graph them and see. If we substitute 0, we get 2 times 0 squared, which is 0. Now, 1 squared is 1, double it is 2. 2 squared is 4, double it is 8. 3 squared is 9, and twice 9 is 18. If we go into the negatives, minus 1 squared is plus 1, double it, plus 2. And you can see this same pattern will extend backwards. You might notice these numbers are rather larger than last time. So much so that I'm not going to be able to graph these ones. But let's have a look. 0. When we go to x equals 1, we've got y equals 2. When we've got x equals 2, we've got y equals 8. Quite a long way up. And here's 8. So this parabola is here. Let's look at this one. 0 squared is 0, half of that's still 0. 1 squared is 1, and half of that is just a half. So we're starting to see a fraction here, or some fractions. 2 squared is 4, half of that is 2. And 3 squared is 9, and half of that is 4 and a half, or if you prefer 4.5. without going into detail, these numbers will match these, because one of the nice things about parabolas is that they are symmetrical. They have symmetry about a vertical axis. At least these ones do. And if we plot these 0, 0, 1 and a half, that's not quite as high as we thought it might have been, 2, 2, and 3 and 4, there's 3, 4, 4 and a half would be there. So it goes across to 3 and up to 4 and a half. So here we go back and up a half. This one will be as high as 2, and this one will be level with 4 and a half back here. Now, normally you wouldn't draw these lines on. Normally they're part of the grid lines on your graph paper, but I just think they're necessary on a whiteboard with no grid lines at all. So there are our two graphs. Well, I've tried to draw the axes the same, and by the way, when you graph, please draw both axes. Always label the axes X and Y, or whatever the relevant letters are, the pronumerals. Always label the origin, and always label at least some numbers on each axis to give a scale. Those things should be always present. Now, I've tried to have them drawn pretty much with the same vertical axis and the same horizontal scale as well. And I think you can see this one's narrower, or taller and thinner or something. This one's a bit more squat. If I go back and I draw on this one our original graph, it went through 1, 1, you might remember, and 2, 4, and 3, 9, so it was further out. That was our y equals x squared graph, and of course it was a bit wide out this way as well. And this one now goes through a half and 2 and 4 and a half further out as well, and this is y equals a half x squared. That's that one. So y equals 2x squared, y equals 1x squared, y equals half x squared. Where do you think y equals 5x squared will be? Well, of course it will be steeper, and then 10x squared will be steeper still. If I gave 1/10 of x squared, then it would be a very shallow parabola going up like this. If I did 1/1000th, it would be extraordinarily shallow and very, very, very slowly rise. Quite interesting. But we're not finished. I want you to notice something of interest. Look at the gaps again. The gap here was 2. The gap from 2 to 8 is 6. And the gap from 8 to 18 is 10. That's not what we had before. We had the odd numbers because we were growing by squares. Building our squares by adding odd numbers. Do you notice, however, what's happened? By doubling everything, we've actually also doubled the gaps between the numbers. Because we've doubled the numbers, everything's spread out. That's 2 times 1, that's 2 times 3, and that's 2 times 5. So we've still got our 1, 3, 5, but they're doubled. So have a look. We can go across one and up 2, across another one, and this time we'll go up 6. 1, 2, 3, 4, 5, 6. And that will give us that graph. What's happening here is we go across by a half, then from a half to 2 is 1.5, and from 2 to 4.5 is 2.5. Now if I double those, I get 1, 2 lots of 1.5 is 3, and 2 lots of 2.5 is 5. It's still our 135, but we've multiplied it by a half. So you can see on this graph we go across 1, and instead of going up by 1 we go up a half, then we go across 1 and up 1.5, and across 1 and up 2.5. From 2 to 4.5 is 2.5. Now that can help us enormously in graphing parabolas. In other words, we can miss out on drawing up our table of values. I'm going to do that one more time, and then that'll be the end of this particular video. and I hope you found that of use. Let's go ahead and do it. Let's imagine that we need to graph y equals 3x squared. And we're going to do it on this graph paper. There's my origin, y-axis. Now, 1, 2, 3, 1, 2, 3. That will be enough scale, you know that they're worth 1 and 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so it would go. Let's see just how much we get. We know that it's going through the origin. That's our starting point. And remember, for our normal x squared graph, our gaps, you can do this in your head or you can write it on paper, are going to be 1, 3, 5, 7. But because we're tripling it, our gaps are actually going to be 3, 9, 15. 3 times each of those. So it means I go across 1 and up 3, 1, 2, 3. Across 1 and up 9. Now that's 3 there. So up 9 is going to get me to 12. Obviously it's a bit pointless trying to go across 1 and up 15. I'll be way off the top of the board. This is very steep. If I go back 1, I go up 3. If I go back another 1, I go up another 9. And again, if I went back 1, I'd go up 15. So we have that same pattern. And if I drew my parabola, it's a bit hard up on a whiteboard, but we'll see. There we go. I've tried to put a rounded tip on the end. I've got my arrows showing that it keeps going forever. And you can see this is in fact, well, it's steeper than our 2x squared from the previous board. There's our 3x squared graph. And we did not set up a table of values because we understood the structure. Cross 1 up 3, cross 1 up 9, cross 1 up 15. Now we're not going to use that all the time. It is important to be able to fill out a table of values, not to ignore them totally. But I did want you to see this structure, and we are going to use this because in our next video we're going to see what happens when we start moving this graph around the coordinate plane. And I think you'll see that there are some nice structures to be found there as well. If you have enjoyed this, please click on the like button below the video. Please leave a comment. I always enjoy reading your comments. And if you're not already a subscriber, then please subscribe to this channel so you can find out about the rest of the videos in this series as they appear. And thank you very much for watching.